Here's the next question, number 12. A steady current I is flowing in the minus x direction through each of two infinitely long wires at y is equal to plus or minus L by 2 as shown in the figure. The permeability of the medium is mu naught. The magnetic field at 0, L, 0 is, well, we have our four options A, B, C, D. Okay, so we have been given just the current which is flowing in the minus x direction. There are two infinitely long wires here at y is equal to minus L by 2 and y is equal to L by 2. And we have also been given the permeability. We have to find out the magnetic flux or the magnetic field density at 0, L, 0. So the basic formula where we have B, and look at the options here. The options are in terms of mu, the permeability, and current. So immediately you should remember the formula B is equal to mu naught into H, where H is the magnetic field strength. So if we find out what H is, then we will be able to find out what B is. Okay, so let's start with H. Now, since we have two infinitely long wires, the value of H would be the magnetic field strength of the first wire added with the magnetic field strength of the second wire. Let me write that down here for you. Okay, so we have H is equal to H1 plus H2. So H1 in terms of current and the radius, we have a general formula where H is equal to I by 2 pi r. Okay, so now let's use this. We get I divided by 2 pi r1 plus I divided by 2 pi r2. Now r1 and r2 corresponds to the length. Now we have two wires. We have one wire at minus L by 2 and another one along L by 2. Now we are to find out at a certain point of 0, L, 0. So in general, let's just take a normal point. We have the origin. We have minus L by 2 here, we have L by 2 here, and then we have L. Now, if we are to find out at this point here, we have to look at two distances. This is our first distance, and this is our second distance. Now, the first distance is L by 2 plus L by 2 plus L by 2. So that's 3L by 2. This entire distance here is 3L by 2. And this distance here is L by 2. That's R1 and R2. So R1 would be I divided by 2 pi into 3L by 2 plus I divided by 2 pi L by 2. Now let's simplify this and see what we get. Let's take I by 2 pi out common. And we are left with 2 by 3L plus 2 by L, right? Taking it up, which becomes the reciprocal. Okay, now simplifying it even further, we will have this as I divided by 2 pi into, now 2 by 3L plus 2 by L results in 6 by, so that's 6 plus 2 divided by 3L, which gives us 8I by 6L. Simplifying it even further, oh there's a pi here, simplifying it even further, we get 4I by 3 pi L. Now there's another thing that we need to remember here. Now because the question says that the current is flowing in the minus x direction, we need to consider the unit the unit direction as well. So this is minus AZ according to the figure over here. Okay, so we are considering the unit direction as well, unit vector minus AZ. So now if H is equal to 4I by 3 pi L times minus AZ, then B can be written as mu naught into H, which is 4 mu naught I divided by 3 pi L into minus AZ. Now since this is a unit vector, we can resolve this as minus 4 mu naught I divided by 3 pi L. Now this is our final expression for the magnetic flux density, and in terms of the options given to us, there we go, it matches option A. Well, I hope this has helped.